Dear learners, I welcome you all to this module. The title of the module is System of Linear Equations, Row Reduction and Echelon Forms. The intent of this module is to introduce the system of linear equations, how to convert it into matrix form and how to solve the system, and also help the learners to know the echelon form and row reduced echelon form of the matrix and how to find the solution of the system using row reduced echelon form of the matrix. Now, we shall look into the systems of linear equations. System of linear equation is the basics of linear algebra. Most of the problems of linear algebra can be reduced into the problem of solving system of linear equations. In this section, we are going to learn about the system of linear equation. A linear equation in the unknowns x1, x2, etc. xn is an equation that can be written in the form a1 x1 plus a2 x2 plus etc. plus an xn, that is equal to b, where xi's ranges from 1 to n are the variables and ai's and b are the constants in the equation. A's are also called the coefficient and b is called the constant term in the equation. Here n can be any positive integer. Note that the degree of variables in the linear equation is always 1. An equation which is not linear is called non-linear equations. We shall see some examples now. Now consider the equation 2x1 plus 3x2 is equal to 5. Here a1 is equal to 2 and the value of a2 is 3 and the constant b is equal to 5. So, this is one of the linear equation, and the next example is x2 plus 9x3 is equal to 0. Here this is an equation with two variables, that is two unknowns. Here a1 is 0, a2 is 1, a3 is 9 and b is equal to 0. The same equation can be considered as an equation with three unknowns where the coefficient of x1 is equal to 0. Now, we shall see some examples of equations which is not linear. x1 x2 is equal to 20. This is a non-linear equation because of the presence of x1 product x2. And the second equation we are going to see is 2 square root of x2 plus x1 is equal to 17. This is also non-linear because of the presence of square root of x2. A system of linear equations is a collection of linear equations with the same variables. In particular, a system of m linear equations in n unknowns x1, x2, etc. xn is given by a11 x1 plus a12 x2 plus etc. plus a1n xn is equal to b1. Similarly, a21 x1 plus a22 x2 plus etc. plus a2n xn is equal to b2, and it ranges from 2 am1 x1 plus am2 x2 plus etc. plus amn xn is equal to bm. So, this is a system of linear equations with m n unknowns and m equations, where here xi's ranges from 1 to n and the other variables, and aij's are also called the coefficient and bi's ranges from 1 to m are called constant terms in the equation. We shall see an example now. Consider the system of equations. The first equation is x1 plus 2x2 plus 5x3 is equal to 5, and the next one is 3x1 plus x2 plus 4x3 is equal to 10. Here we have three unknowns and we have two equations. A solution for the system of equations is a list of values for the unknowns which is a solution of each of the equations in the system. The set of all possible solutions of the system is called the solution set or the general solution of the system. A system of linear equations can either have no solution or exactly one solution or unique solution or infinitely many solutions. So, which means that a system may or may not have solution. The system of linear equation is said to be consistent if it has one or more solutions, and it is said to be inconsistent if it has no solution at all. Two systems are said to be equivalent if they have same set of solutions. Now we have system of linear equations here, m equations and in n unknowns. As we have already seen, this has a general form and can be put together like this, that is a11x1 plus a12x2 plus etc. plus a1nxn is equal to b1, a21x1 plus a22x2 plus etc. plus a2nxn is equal to b2, and then the last equation is am1x1 plus am2x2 plus etc. plus amnxn is equal to bm. So, now note that if all of the bi's, that is constants, are equal to 0, then we call the system of linear equations as homogeneous linear equation. If at least one bi is not equal to 0, then we can have this as a non-homogeneous system of linear equation. Both homogeneous and non-homogeneous can be solved. Now, how are we going to solve the system of linear equations? As we have already stated, a solution to the system of linear equations means the list of values for the variables, that is for the unknowns xi's, so that if we substitute the values here, all of the equations should get satisfied. So, that is what we mean by solution. How are we going to solve the solution? We are going to solve here, we are going to solve using two methods. The first one is elimination method, and then we are going to solve using matrix form. So, first we are going to use the normal method, elimination method. So, from the word itself, it states we are going to eliminate some variables one by one, and then we are eventually we are going to arrive at a solution. Okay. So, before moving to the example, now let us talk about some notation on matrix. So, first we shall talk about the coefficient matrix. So, this here A11, A12, etc. A1n, or in fact A21, A22, A2n and AM1, M2, AMN, all of them are called as the coefficients of the variables. The coefficient of x1 in the first equation is A11 and the coefficient of x2 in the mth equation is am2. So, all of the ai's are coefficients. So, if you are going to form a matrix using only the coefficients, then that is called as a coefficient matrix. For example, the coefficient matrix will look like this. So, from here to here, a11, a12, etc. a1n, a21, a22, etc. a2n, am1, am2, etc. amn. It is a m by n matrix. You have m rows and n columns. So, that is what we mean by coefficient matrix. And after that, we are going to talk about another notation called augmented matrix. So, usually augmented matrix is formed like with the notation called within the square bracket we used to write a comma b. Now, I have given another notation variable here m, and together with coefficient matrix, if you add another column with the constant terms, then that matrix is called as an augmented matrix. This is AUGMENTED, augmented matrix. So, that is here, and with the help of the augmented matrix, we are going to solve the system of linear equation. Now, we shall start with an example. So, here we are asked to solve the system of linear equation. Here we have how many equations? We have 3 equations and 3 variables. We have 3 equations and 3 variables. So, the first equation is 2x1 minus 4x2 plus 2x3 is equal to 0, x2 minus 4x3 is equal to 4, minus 4x1 plus 5x2 plus 9x3 is equal to minus 9. So, I am going to denote these 3 equations like 1 with the circle encircled, and 2 and the encircled, and 3 we are enclosing this with the circle. So, this is how I am going to denote the equation. So, now as I told, first we are going to solve this using elimination method. Elimination in the sense that here we will be focusing on the third equation and we try to eliminate the variables, maybe x1, x2, and then we eventually get one variable and the value of that variable. So, whenever you eliminate a variable from an equation, the system of equation will also get reduced or will also get altered. So therefore, if you are going to consider 1, 2, 3 now, then after elimination, you are going to consider 1, 2, the whatever you have obtained while during the first elimination, that equation you have to consider, and you have to proceed in the similar way, and that will lead to a solution. So now what I am going to do is I am going to consider the first equation and the third equation. I am going to multiply the first equation by 2 and I am going to subtract it from the equation 3, so that this x1 variable will get eliminated from the third equation, or I can easily eliminate the x1 variable. So here you can see if I multiply by 2 here, I will have 2 multiplied by 2 4, and minus 4 I have here, and what I can do, I can simply add them together. So it is not subtracting, you can add them together. So now this is minus 4x1 plus 5x2 plus 9x3 is equal to minus 9. I multiplied first equation by 2, and then I am getting 4x1 minus 8x2 plus 4x3. Now if I add them together, I have minus 3x2 plus 13x3 is equal to minus 9. You can see here a variable is eliminated, a variable called x1 is eliminated, and after that it is your choice, you can consider first equation, second equation and the fourth equation as again a system of equations. So now I have named this the equation that I have got as the fourth equation, and then what I am going to do is I am going to work with the second equation and the fourth equation. I am going to multiply the second equation by 3. I am going to add it together with the fourth equation. As you can easily see here, my fourth equation has minus 3 as the coefficient of x2, and look at the second equation has only 1 as the coefficient of x2. So in order to eliminate x2, it would be very helpful if you multiply the second equation by 3 and add them together with the fourth equation. So that is what we are going to do now. If you do like that, you will have the value of x3, the x3 is equal to 3. So you have already eliminated x1, and now you are getting the value of x3 is equal to 3. And what you can do now, you can substitute the value of x3 is equal to 3 in the second equation, that will give you the value of x2. So now right now you have the value of x3 and x2, no problem, you have only one variable left to find, and you can substitute these two variable values in any of the equations. You will get your answer. That is, I am going to substitute either in 1 or in 3, that is your choice. Here I have substituted the values of x2 and x3 in the first equation, that is giving me the value of x1, that is equal to 29. The solution is x1 is equal to 29, x2 is equal to 16 and x3 is equal to 3. So this is how we have obtained the solution, and as I told you earlier, a solution is a list of values for the variables that satisfy the entire system of equation. So if you substitute the values of x1 and x2 and x3 that we have obtained from this problem in the given original equation, then your equation will get satisfied. And yeah, that is what we mean by solution. And it not necessarily, in reality we don't have solution for some equation, not necessarily an system of equation have solution. It may have solution or it may not have solution. So if at all it has a solution, the solution also need not be unique. It may be unique exactly one solution, or it may have more than one solution, or it may have finite number of solutions, or in fact it may also have infinite number of solutions. So this is one method of solving system of linear equations. And then we are going to solve the same system of linear equation using matrix method, that is we are going to make use of the augmented matrix that we have talked about. So now coming back to here, so first with the help of these equations we are going to form an augmented matrix, and we are naming this as A, but if you want you can have this, that is M also. So now the augmented matrix is 2 minus 4 2 0 0 1 minus 4 4 minus 4 5 9 minus 9. How did I form this matrix? So the first 3 rows and 3 columns or the coefficient matrix, and together with this I have added one column with all the constant terms. So, the coefficient of x1 is 2, coefficient of x2 is minus 4, coefficient of x3 is 2 and the constant here is 0. And similarly, I do not have any x1 term here, that means that the coefficient is 0. I have added 0 here, and then the coefficient of x2 is 1 and the coefficient of x3 is minus 4 and the constant is 4, and in the third equation I have the coefficient of x1 to be minus 4, coefficient of x2 is 5, coefficient of x3 is 9 and the constant is minus 9. So, now I have formed an augmented matrix. Now, I am going to reduce this matrix in order to get a solution. So, how am I going to do that? So, I am going to this first row I am going to note by the notation called R1, that indicates row 1, and the second row R2, and the third row I can call that as R3. So, now the same procedure, but not not explicitly writing as an equation. I can first changing R3 by adding 2 multiplied by R1, that is R3 gives is equal to R3 plus 2 R1. So, I am going to have my R1 as a constant term as such, and R2 I am not going to touch, but R3 is going to change like R3 plus 2 R1. So, here I have minus 4 plus 2 R1. So, that will give me here I will be having a 0, right. So, yeah, this same matrix is repeated here, but what I am going to do is I am going to add 2 R1. Therefore, minus 4 plus 2 R1, that is plus 2 multiplied by 2, I will have 0 here, the first, this one is wrong, I will be having 0 here, and then 5 plus 2 R1, that is 5 minus 4 multiplied by 2, that will give me minus 8, 5 minus 8, I will have 3 here. Therefore, the first entry is 0, second entry is 3, like that I will have. And after that, after finishing this step, I am going to again change R3, I am going to add with R1, that is multiplied by 3. R3 gives R3 plus 3 R1, that is giving me this matrix. As you can see here, I am having, this is an upper triangular matrix, all the entries of the above the diagonal has values. So, I have 0 0 0 here, and then I am going to change R2 to be equivalent to R2 plus 4 R3, and I am doing that, and R1 I am going to change, that is minus 2 R3 plus R1, I am getting this matrix, and after that I am changing R1 to be 4 R2 plus R1, and then R1 to again 1 by 2 R1. So, why am I doing like this, and do I have to memorize all the transformation or the reductions, row reduction that I am applying? You need not, right? So, because this you have to have in your mind that what is that you want at last. So, here my aim is to, my strategy is to make the matrix that is the augmented matrix, in fact the coefficient matrix that I am considering, that to be an identity matrix, so that I will be able to get the value of the variables. So, that is what my strategy is now. Therefore, I am doing an operation such a way that if I transform a row, I should have the identity matrix. That is how I am moving. So, therefore, an element, if you add 2 rows, that does not change effect, has any effect on the value of the variable. Therefore, I am making all the elementary row transformations in order to get identity matrix from the given matrix. That is my strategy. Therefore, I am doing whatever it takes to convert the given matrix into an identity matrix. So, at last I have an identity matrix here and with some coefficients. So, here I have, therefore, which means that, so this one corresponds to the variable x1, right. Therefore, x1 is equal to 29 and x2 is equal to 16 and x3 is equal to 3, or in fact, you can again bring back to this form, ax is equal to b 1 0 0 0 1 0 0 0 1 x1 x2 x3 29 16 3. From here also you can say x1 is equal to 29, x2 is equal to 16, x3 is equal to 3, and therefore, it has a solution, that too unique solution. Therefore, the system is consistent, as it is consistent, it has a unique solution. And is this the only method of solving a system of equation using a matrix method? It we have so many, but this also you don't have to always convert into an identity matrix. In fact, you can have 2 here, you can have 3 here, you can have 4 here. So, if you have 2 here, then 2x1 will be equal to 29 and x1 will be equal to 29 by 2. In that method also you can do. All you have to do is you have to apply some elementary row operations in order to get your matrix in a easier, simpler way, so that you will be able to solve the system of linear equations. So, now we have seen an example of a system of linear equation that has a unique solution and that is consistent. Now, we have already stated that a system of linear equations may not have solution at all. In that case, or in that scenario, we will call the system of linear equations as an inconsistent system of linear equations. So, in other words, what do we mean by a solution of two linear equation in variables x and y? So, we mean that if you have a two linear equation in x and two variables, maybe x and y, and the two linear equation will definitely have will be a straight line, and if these two straight line intersects at a point, that intersecting point is called as a solution of the system. So, it may have a single intersecting point, or it may have two intersecting point, or it may not intersect at all. It may be intersecting at infinite number of points. Therefore, if you have two parallel equations, what happens? If you have two parallel equation never intersect, right? Therefore, that parallel equation does not have parallel straight lines, does not have any intersecting point. Therefore, corresponding to this parallel straight lines, if we consider the equation, that is linear equation, those linear equations are not going to have any solution. Therefore, that system forms an inconsistent system. That is what we have in the next example. We have considered 3x plus 2y is equal to 12, and other equation 3x plus 2y is equal to 6. So, this can be written in the form Ax is equal to b, and from here we can form an augmented matrix, and then this is our augmented matrix 3 to 12, 3 to 6, and if you try to reduce all the variables will become 0, 0, 0 in the second row. Therefore, it has an inconsistent solution, or in fact no solution at all. So, here you can see the graph, the corresponding to these straight equations I have drawn straight lines, and these two straight lines are parallel, and it is not gonna intersect. Even if you extend it to an infinite number of terms, it is not gonna intersect. We don't have any intersecting points. Therefore, it doesn't have any intersecting point, which means it doesn't have any solution. The system is inconsistent, and the problem is over now. And if you, this is just an interpretation of a system having one solution. Again in two variable form. If you have x, y as two variables, and this is one equation, this is another equation, and you can see it intersects at a single point. Therefore, we call this as a one solution system, that is unique solution system of equation, and this is consistent. And then you can have another equations, another set of system of equations. So, the black line indicates one equation, and below that you can see another red line that also indicates another equation. You can see here one equation is touching at so many points of the other equation. It exactly lies upon the other equation. Therefore, if you gonna find the intersecting points, we cannot count, right? It is infinite number of intersecting points, but it definitely has intersecting point, but the number of intersecting points is infinite. Therefore, this also has a solution, but the solution is not unique. It has infinite number of solution, and this is again a consistent system of solution. Both this and this are consistent, and this is inconsistent system of solution. Now, we shall discuss about row reductions and echelon forms in a detailed manner. Here, we are going to introduce the necessary matrix concepts for solving the system using matrix. The concepts such as echelon matrices and elementary row operations are also of independent interest. We shall see a definition now. A matrix is said to be in echelon form or row echelon form if it satisfies the following properties. The first property is 0 rows, if any, or below all non-zero rows of the matrix. Second property, each leading non-zero entry, that is first non-zero element in a row, is to the right of the leading non-zero entry in the row above it. All the entries in a column below the leading non-zero entry should be 0. So, these are all the three property, and addition to these conditions, if a matrix satisfies two more conditions, that is each leading non-zero entry equal to 1, each leading non-zero entry is the only non-zero entry in that column, then the matrix is in row reduced echelon form or reduced echelon form. That is what we have seen in the example that we have discussed. If the matrix satisfies row echelon form, then it is said to be row echelon matrix. If the matrix satisfies row reduced echelon form, then the matrix is called row reduced echelon matrix. The main difference between an echelon matrix and a row reduced echelon matrix is, in an echelon matrix, there must be zeros below the leading non-zero entries, but in a row reduced echelon matrix, each non-zero leading must be zeros above the leading non-zero entry. The zero matrix and the identity matrix are the examples for row reduced echelon form. We shall see some examples now. Consider the first matrix. The first row is 3 to 1, second entry is 0, 1, 2 by 3, third row has 0, 0, 2. So, this is in echelon form, and we have other matrices 1, 0, 0, 2, 0, 1, 0, 4, 0, 0, 1, 4. These are also in echelon form, but the second one is row reduced echelon form. And another example. So, consider the matrix 1, 1 by 2, 3, 7, 0, 2, 2, 0, 0, 0, 0, 0, 0, 0, 0, 0, the first matrix, and the second matrix that is mentioned on the screen are also in echelon form. Any matrix can be row reduced into more than one matrix, and the echelon form is also not unique, but uniqueness holds for row reduced echelon matrix. We shall see a theorem now. The statement is, each matrix is row equivalent to a unique row reduced echelon matrix. The position of leading non-zero entry will not change if reduce an echelon matrix into a row reduced echelon matrix. A definition says, a location that corresponds to leading 1 in the reduced echelon form of a matrix is called the pivot position or pivot position, and the column of a matrix that contains a pivot position is called a pivot column. The leading non-zero elements in pivot position that is used to create zeros using row operation are called pivots. An example we shall see now, row reduce the given matrix into reduced echelon matrix. So, the given matrix is 1, 2, 3, 4, 4, 10, 12, 16, 6, 8, 20, 24. We shall solve this. First pivot column is column 1, that is C1, and first pivot element is 1. Convert all these entries in C1 other than 1 into 0. Do the corresponding operations. The first one is R2. R2 is changed to 4R1 and R3 is changed to R3 minus 6R1. This gives us the matrix 1, 2, 3, 4, 0, 2, 0, 0, 0, minus 4, 2, 0. The next pivot column is second column, and the pivot element is second element in the second column. Convert the other elements in C2 by using pivot element. That is, R1 is changed to R1 minus R2, R3 is changed to R3 plus 2 R2. Therefore, that given matrix is equivalent to the matrix 1, 0, 3, 4, 0, 2, 0, 0, 0, 0, 2, 0. Now, consider the column C1 as the pivot column and convert the other entry 0 using the pivot entry true. That is, change R1 to 3 by 2 R3, and the given matrix will be equivalent to the matrix with the entries of the first row as 1, 0, 0, 4, and the second row 0, 2, 0, 0, and the last row is 0, 0, 2, 0. Now, convert all the leading entry to 1. The following operations you can apply, that is R2 changed to 1 by 2 R2, R3 is changed to 1 by 2 R3, that will give you the matrix with the entries 1 0 0 4, 0 1 0 0, 0 0 1 0. This is the row reduced echelon form of the original matrix. We shall see a theorem called existence and uniqueness theorem. A linear system is consistent if and only if the rightmost column of the augmented matrix is not a pivot column. That is, if and only if an echelon form of the augmented matrix has no row of the form 0 0 0 b with b non-zero. If a linear system is consistent, then the system has either a unique solution when there are no free variables or infinitely many solutions when there is at least one free variable. We shall see an example, and we are going to find the general solution of the given linear system using row reduced echelon form of a matrix. The system is given on the screen, you can see now. Okay, for the solution, we are going to first form the augmented matrix of the given system. The augmented matrix is also on the screen, you can see, and we are going to apply the row transformation. If you apply the corresponding row transformation, you will get the corresponding matrix, and in general solution at last you have x1 to be equivalent to 1 minus 10 x4, x2 is equal to minus 3 minus 4 x4, x3 is equal to 2 plus x4, and here x4 is a free variable. As we have already stated, here we have one free variable x4. That means that this system is going to have infinitely many solutions. That is, this solution is called a general solution of the system because it gives an explicit description of all solution. Particular solution is given by setting any value to x4. Therefore, if you set x4 is equal to 1, then you have a solution for all the variables. X1 is equal to minus 9, x2 is minus 4, x3 is 3, again x4 we have set to be 1. And if you change x4 to another value, corresponding to that value, you have another system of solutions. Therefore, the particular problem has infinitely many solutions and the system is consistent. Dear learners, now we are going to conclude the module. So, in this module, we introduce the system of linear equation and we have seen how to convert a system into matrix form and how to solve the system also. We have discussed so many examples. We also discussed echelon form and row reduced echelon form of the matrix and how to find the solution of the system using row reduced echelon form. So, we have seen that a system may or may not have solutions. I think this module will be very helpful to you. We will see in the next module. Until then, thank you.